Hello, Namaskara. I am P.R. Hampiholi, Head Department of Mathematics, KLS Bhakti Institute of Technology, Belagavi. Under the platform of e-Shikshan, under the umbrella of VTU, we are learning third semester engineering mathematics, 18 Mat 31, third module, Fourier transforms and Z transforms. This is my 10th lecture. So, welcome to 10th lecture of 18 Mat 31 third module, Fourier transforms and Z transforms. So we have learnt a lot of concepts in Z transforms also. I want to, before I go to some important theorems which are known as initial value and final value theorems, I want to complete these two examples. Our ultimate aim is to solve some differential equations, or they are known as difference equations. So find Z transform of Z transform of 1 by n plus 1. This is what is the corresponding Z function of this. Now, in the definition, we use a direct definition. Z transform of any function is to that function you are multiplying by a Z function, adding all these from n equal to 0 to infinity. Now, whatever the function is given to us, this becomes our n function un. So that has to be substituted here. So now z of un therefore equal to summation of n equal to 0 to infinity 1 by n plus 1 z raised to minus n. Again, the fundamental is after the transformation, our basic aim is transform n to z function. After the transformation, there should not be any n function. There should be only constants and z functions. Now, what I do is I'll go on putting n equal to 0, n equal to in these 2 points, n equal to 0 here, n equal to 1, n equal to 2. Let us observe what we will get. If I put n equal to 0, z raised to minus 0. If I put n equal to 0 here, z raised to minus 0, here 0 plus 1. So that first term after n equal to 0, z raised to minus 0 by 1 plus z raised to minus 1 upon 1 plus 1, 2 plus z raised to minus 2 upon 3 and up to infinity. And if this becomes 1, z raised to minus 0, this is 1. So I can write this as first term as 1, second term as 1 upon z upon 2, 1 upon z whole square upon 3. Let me write one more, 1 upon z raised to 3 upon 4 and so on. Now what I will do is I will multiply and divide by z. So if I multiply and divide by z, outside I will retain z, and inside what happens is I have to divide by z. Inside I have to divide by z. So this becomes 1 by z. So 1 by z whole square, 1 by z upon 1, 1 by z whole square upon 2, 1 by z whole cube upon 3. That is inside the bracket we multiplied by 1 by z. Outside the bracket, to compensate that, we multiplied by z. So one more raised to 4 upon 4. So this reminds us of some formula for infinite series. So this is what we are doing is for Z transform of 1 by n plus 1. Now if I remind you a formula, what is that formula? Log of 1 minus x is minus x minus x square by 2 minus x cube by 3, means all powers 1, 2, 3 are there, corresponding denominators are there, minus x raised to 4 by 4 and so on. So this is equal to, if you take minus sign common, x by 1 plus x square by 2 plus x cube by 3 plus up to infinity. Now if you compare these two terms, what we can compare is, this is x square, so that only thing is x looks like 1 by z now. So can we now, therefore our z transform of 1 by n plus 1 start looking like this. Outside z as it is, the bracket is minus of this, I can write this minus and I can transfer this side, minus of log of, because the value of this bracket is minus log of 1 minus x minus log of 1 minus, instead of x I have to write 1 by z. So now everything is converted in terms of z. Right hand side is z, left hand side is n plus 1. So that is n function. After transformation, this minus sign I can drag out, minus z, and inside I can simplify, so that z transform of a n function, therefore we found it as this as the answer. So sometimes we are given discrete values. The next example, sometimes we are given discrete values, we should be able to do that z transform also. This is altogether a different example. If sometimes some important examples I am repeating, 1 or 2 here and there in the last class also, if it is done, this is for the use of you all. If u naught or if un is a set of even numbers 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, then what is the u of z function, corresponding z transform of this. Now as a solution part, z transform of any n function is summation n equal to 0 to infinity. To this un you are multiplying z raised to minus n. Shall I expand it now? First one is u naught z raised to minus 0, u1 z raised to minus 1, u2 z raised to minus 2, u3 u naught u1 u2 u3 u4, u3 z raised to minus 3 plus u4 z raised to minus 4 up to infinity like this, or still in a better form, u naught plus u1 by z plus u2 by z square plus u3 by z cube plus u4 by z raised to 4 and so on. Now in the given scenario, we are having u naught, u1, u2, u3, u4, so that you should write that since we are given un as set 2, 4, 6, 8, 10, we can write u naught, u1, u2, u3, u4 as 2, 4, 6, 8, 10 and substitute these 2, 4, 6, 8, 10 here, that completes our work. So now Z transformation of, therefore Z transformation of given set, discrete set is 2 plus 4 by Z plus 6 by Z square plus 8 by Z cube plus 10 by Z raised to 4. That's all. So this finite function, because it has got finite value, we will get a finite series. If it is infinite values, we get infinite series. This becomes the answer. Now before I proceed to the next type of examples, examples means at last what we are doing, converting n type of functions to z type of functions. In the next class, reverse, z type of functions to n type of functions we are converting. All knowledge we are using to solve so-called differential or difference equations of discrete values. I need two important theorems, and they are known as initial value and final value theorems. Initial value means u0, final value means u infinity. Of course, we can find u1, u2, u3 also using our right shifting, left shifting theorems. Now, what this tells is, first one is, suppose you are asked to find, right, state and prove initial value theorem. They may stop here, sometimes they may write of Z transforms, because in your question paper this is the only initial value theorem, so here they may stop. The solution is, or the theorem is, statement if at all Z transformation of certain n function is u of z, then it tells that first value u0 is nothing but just take the limit of right hand side as z tends to infinity, so that we can write. Now a small proof is there, just for the sake of proof. Sometimes, now usually you are not asked the proof nowadays, but for the sake of proof, which are very nice here, we know that u of z is z transformation of some n function, means it is summation n equal to 0 to infinity, which is un z raised to minus n. That is u of z equal to, if I expand this, it is u0 plus u1 z raised to minus 1 plus u2 z raised to minus 2 plus u3 z raised to 3 plus and so on. Now if I take infinity as the limit, some constant divided by infinity, here all 1 by infinity, second term onwards 1 by infinity, they become 0. That is, if you note it, this part, this part remains, and the remaining part, this part, each term becomes 1 by infinity. Okay, 1 by infinity becomes 0. So let us take the limits then. Limit of left hand side as z tends to infinity equal to limit of right hand side as z tends to infinity, u0 plus u1 by z plus u2 by z square plus u3 by z cube and so on. We assume that u0, u1, u2, u3 are finite constants. So that second term is 0, third term is 0, fourth term is 0. So we are left with constant remains as it is. Remaining parts are zeros. So that if I reverse the sides, u0 is nothing but a limit as z tends to infinity of the entire z function. That is, without knowing n function, we can find u0 is the beauty of this theorem. Similarly, a little bit different from this, little bit inward proof. State and prove final value theorem. So theorem is if then here, if z transformation of un function, suppose is some z function, then okay, u infinity means last term means it is usually we don't write this limit of nth term as n tends to infinity. As n tends to infinity, this becomes u infinity is given by not directly taking infinity for this, but after multiplying by z minus 1 and after taking not infinity, after taking limit as z tends to 1. So don't get confused here. Left hand side is notation for u infinity. Left hand side is notation for u infinity. So u infinity is important here. U infinity is z tending to 1, z minus 1, u of z. Now here the proof is very interesting. Now we know that consider z transformation of n plus 1th term minus nth term. Z transformation means what? Z transformation means what? Whatever the function is there inside this bracket, whatever the function is there inside this bracket, we multiply by z raised to minus n and take the limit. Now z transformation is linear. Z transformation of first function, z transformation of second function, z transformation of first function minus z transformation of second function equal to let me keep in the beginning as it is, n equal to 0 to infinity. Just download this as it is, un plus 1 minus un z raised to minus n. Now because of the shifting theorem, you can write this as first one. Okay, this is z into u of z minus u naught as the first one minus second one as it is minus z of un as it is. Z of un is uz only. We can write this as u of z. Okay. So let me write z of un, you can write it as u of z. Still I don't want to change this right hand side, un plus 1 minus un z raised to minus n. Now here in this case there are two u of z values. If I take u of z common, what remains is z here and minus of 1 here. So that is in the theorem z minus 1 is there. This term remains minus z into u naught minus u naught z remains. Now it is the time to expand. Right hand side also. Okay. Put n equal to 0, or you can go on putting You can go on putting summation n equal to 0 to infinity un plus 1 minus un z raised to minus n. Suppose now I think of making this right hand side as this part as 1. If at all I want to make this part as 1, I have to put z equal to 1. That is, it is putting z equal to 1 is equivalent to limit of z tending to 1 of left hand side is same thing as limit of z tending to 1 please of z tending to 1 number of right hand side is summation n equal to 0 to infinity un plus 1 minus un z raised to minus n. Now left hand side there are two terms, limit of first term minus limit of second term. So limit of first term I will keep as it is because it is the left hand side of the theorem main statement. Minus if I put z equal to 1, it becomes u naught equal to right hand side when I put z equal to 1, this part becomes 1. So limit of z tending to 1 becomes, it is nothing but summation n equal to 0 to infinity un plus 1 minus un. Now there is no limit in the right hand side. I can go on expanding the right hand side, which is n equal to 0, it becomes 1 minus 1 and 0 combination. N equal to 0, next add n equal to 1, 2 and 1 combination. Like that, 3 and 2. Now you can observe that limit of z minus 1 into u of z as z tends to 1 minus of u naught, u1 and u1 are getting cancelled, u2 and u2 are getting cancelled, u3 and u3 are getting cancelled. Your intuition tells that, here you need intuition. For first term there is no cancellation term. Similarly for last term also there will be no cancellation term. So remains is last term and the first term minus u naught. But left hand side also we have got minus u naught, right hand side also we have got minus u naught. Both of minus u naught if we cancel, instead of writing u infinity, we write nth term tending to infinity. So u infinity means last term final value theorem, or un as n tends to infinity. Both of these are same, equal to this part, equal to remaining part, which is a limit of z tending to 1, z minus 1, u of z. Especially now we are going to use u naught value. Remaining u1, u2, u3 we have already learnt in the shifting theorem. Here we go for next set of important examples. So let us take next set of important examples. Suppose now this whole thing is done. If at all you are given un equal to n square 1 by n plus 1 and so on, you can find u naught, u1, u2, u3. But corresponding z function if you are given something like z square minus z upon z minus 1, z minus 2, z minus 3 and so on, directly can you find u naught, u1, u2, u3 without knowing un? That is what we want. So this theorem now, initial value and final value theorem along with shifting theorems are going to help. These examples are from u of z to u naught, u1, u2, u3 and so on directly. Okay, u of z to this examples. First example, many times such examples are asked, please practice them. If u of z is something like 2 times z square plus 5 times z plus 14, write down very carefully, divide by z minus 1 raised to 4, then Then just neglect this part. Neglect this part now. This was explanation part. Then find u0, u1, u2. If possible, let us find u3 also. Or sometimes you are not given to find u0, u1. You are not asked to find u0, u1. Just or you may be asked find u2, u3 directly. But directly u2, u3 you can't find. To find u2, u3 you have to find u0, u1, u2. So let us start. How do you find the solution? First of all, you write we are given some z function. Without fail, copy it properly. 2z square plus 5z plus 14 all divided by some z minus 1 raised to 4. Now here some basics. So whenever I write, even I can write this as basic is if the highest power of z here is less than the highest power of z here, highest power is z raised to 4. Always as n tends to infinity, always as z tends to infinity, if the numerator divided by denominator, if denominator highest power is more than numerator, then always this tends to 0. And reverse, it tends to infinity. If they are equal, then the coefficients of highest powers. But here at a glance you can tell, as it is if you take the limit, it is z square by z raised to 4, 1 by z square becomes 0 as n tends to z tends to infinity. Now for u0 is nothing but directly you take limit. Before u0, let me write u of z once again. Before u0, let me write u of z once again. If I take z square common here, what I get in the numerator is 2 plus 5 by z square is 5 by z plus 14 by z square. In the denominator if I take z raised to 4 common, this looks like 1 minus 1 by z raised to 4. Or in a still better way, we can write it as u of z also can be written as simplifying this part 1 by z square into bracket 2 plus 5 by z plus 14 by z square whole divided by 1 minus 1 by z raised to 4. Now for u0 is directly limit of u of z as z tends to infinity, which is limit of whatever you have written just now, limit of all these directly. Let us observe what happens to this limit. Limit as z tends to infinity, whatever is there you just copy paste here, 1 by z square into square bracket 2 plus 5 by z plus 14 by z square whole divided by 1 minus 1 by z raised to 4. Now when I take the limit, we can observe that z tending to infinity means 5 by infinity is 0, 14 by infinity is 0, 1 by infinity is 0. So only 2 remains. At last 2 divided by infinity also becomes 0. So hence this u0 becomes 0. Now u1, there is a formula for u1. u1 is a limit as z tending to infinity, shifting theorem, z into u of z minus u0. So now already u0 is 0. What else you have to write? Is limit of z tending to infinity, z into u of z is 1 by z square. This u of z I am writing 1 by z square 2 plus 5 by z 14 by z square. Once again I am telling this u of z we are writing 14 by z square whole divided by something bracket raised to 4 1 minus 1 by z raised to 4. Now to be noted is this 1 by z, the simplification of this becomes 1 by z. So now if I continue, this looks like a limit z tending to infinity of simplification of this is 1 by z. Remaining let us not touch it. 2 plus 5 by z plus 14 by z square whole divided by something raised to 4, which is 1 minus 1 by z raised to 4. Now we are ready to take the limits. Taking the limits means, in a simple sense, wherever z is there, you have to go on putting infinity. Now this is 5 by infinity 0, 14 by infinity 0, 1 by infinity 0. At last this becomes 2 by infinity also 0. That is what we are calculating. We are calculating u1. So u1 also becomes 0 in this case. So in this case both u0 and u1 became 0. This example, many times such examples asked. u2 equal to, u2 is nothing but, you can again apply shifting theorem, limit z tending to infinity of z square, okay, u of z minus u0 minus u2, u1 by z minus u2 by, or u1 by z, you can write, you can stop here. So let us see what u2 value we start getting. What is the u2 value you start getting? This is equal to both u0 and u1. Just now we found that they are zeros. Limit as it is, z tending to infinity as it is, and z square as it is. U of z, let me remind, u of z, this is our u of z. This I have to copy paste. So if at all I copy paste that, 1 by z square 2 plus 5 by z plus 14 by z square whole divided by 1 minus 1 by z raised to 4 minus, this is our u of z, whole thing is u of z I wrote, minus u0 minus u1. Now it is very crystal clear that limit of z tending to infinity, very clearly you can see that these two z square terms are getting cancelled. So whatever remains is 2 plus 5 by z, except 2 remaining are becoming 0 after taking the limits, is also very crystal clear. Denominator becomes 1. Now if I take the limit, as we observed, 5 by infinity is 0. Limit means whatever infinity is there, z you have to put infinity, 5 by infinity, 14 by infinity, 1 by infinity is 0. So 1 raised to 4. So we are going to get this limit, taking limits, taking limits. 2 plus 0 divided by 1 minus 0 raised to 4, which is telling you the value of u0. Up to u0, u1, u2, of course, we don't have much problem of simplification. So I'll rewrite the values for our next reference. u0, u1 0, u2 equal to 2, because for u3 we need all these values. For u3 it is again limit of z tending to infinity. So can you remind u3? u2 was this was our u2 value. Very similarly, can we write u3? u3 means here z raised to 3, u of z, u0, u1, one more term will come. Whatever is there here, one less than that, 1 stops here. If it is 2, it stops at 1. And whatever the coefficient u2, 2 is there, z square will come. If 3 is there, z cube will come. So let us use that property of u3. u3 equal to z cube into bracket, whatever the mean u of z is there, for that you have to subtract u0, u1, u2 terms, u0, u1, u2 terms, and take the limit as z tending to infinity. Now u0 0, u1 0, u2 equal to 2. Just here above the head of this, whatever I made the right mark, here it is written. So let us not delay, substitute here limit as z tending to infinity of z cube into bracket. U of z also we have written 1 by z square. So we have to copy paste this again, this part. Okay, 1 by z square, 2 plus 5 by z, 14 by z square, 2 plus 5 by z plus 14 by z square, whole divided by 1 minus 1 by z raised to 4. Sorry, still u0, u1, u2 value remain. Minus u0 value minus u0 value 0, u1 value 0, u2 value is 2 divided by z square. Now here we have to make little effort of algebra, which is equal to limit as it is, z tending to infinity as it is, limit as it is, z tending to infinity as it is. So these two become z. Inside again, inside this flower bracket, z cube as it is. Inside the z cube as it is, let us keep first. Inside the flower bracket, here, if I simplify this is nothing but LCM is z square into 1 minus 1 by z raised to 4. And here need not multiply. 2 plus 5 by z plus 14 by z square. And here please minus 2 times this bracket raised to. Now little carefully equal to limit of z tending to infinity, z cube, denominators as it is, z cube as it is, denominators you can write, of course you can make it z raised to 1, 1 minus 1 by z raised to 4, in the square bracket 2 plus 5 by z plus 14 by z square. There is a small expansion of this, which is 1 minus 4c1 means 4 by z plus 6 by z square, because 4c2 it is 4c0, 4c1, 4c2 minus again 4c3, 4 by z cube plus 4c4 means 1 by z raised to 4. This is expansion of a minus b raised to 4 using binomial expansion. Now to be noted is plus 2 and minus 2 getting cancelled. Remains is 5 by z. This is important for us. 5 by z and minus 2 and minus 4. 8 by z. 5 plus 8, 13 is important. Now because when I subtract, when I multiply by this z, what happens? Okay, when I multiply by this z inside, of course before multiplying only plus 2 and minus 2 you got cancelled. Remains is z into bracket 5 by z plus, of course, 5 by z plus 14 by z square minus minus 4 by z plus 6 by z square minus 4 by z cube plus 1 by z raised to 4 whole divided by at bracket raised to 4. Let us keep as it is. Here a simple thing we have to observe that denominator is as z tends to infinity is, this becomes 1 minus 0. When I multiply by z, only the first term here and only the first term here are going to become constants. This 2 is forgotten. Remaining 14 by, when you multiply by z, denominator z remains 14 by z. Here also denominator z remains. So that which all terms remain in denominator z, this term, this term, this term, this term, after multiplying by z also denominator z remains. So whichever is not remaining is 5, this becomes 5 and this becomes plus 8, 5 plus 8, 13. So what I'll do is, without wasting much time, the answer is 13. Okay. So this you have to practice a bit. Let us take quickly one more example of the similar case. One more example of the similar case. Example number 2. If u of z is equal to, okay, 2 times z square, something you can write, 2 times z square plus 3 times z plus 4 whole divided by z minus 3 raised to some 3, suppose z minus 3 raised to 3. So now find u0, u1, u2, if it is possible u3 also. Now as it is, z square and z cube combination tells that it is almost z square by z cube if you take the highest powers, and 1 by z means u0 becomes 1 by infinity 0 at the outset only. Okay, so from u1 onwards you will get non-zero. That is solution part. Given u of z equal to 2z plus 3z square, 2z square plus 3z plus 4 whole divided by z minus 3 raised to 3, or this can be written as, taking z square common here, numerator becomes 2 plus 3 by z plus 4 by z square whole divided by, here you can take z common, becomes z cube outside, z raised to 3 will come outside, 1 remains here, minus 3 by z. It is a question of algebra. So that we have got two ways of writing this z function. One way is, this is our u of z, if at all it is useful to us. One way is, this is our u of z, cancelling this z square and z cube, making it 1 by z, 1 by z into 2 plus 3 by z plus 4 by z square whole divided by something raised to 3. Denominator is usually, limit becomes 1. In that way it is adjusted. Now let us go for u0. So if it is directly u2, u3 is asked, we have to find u0, u1 always. So first, without fail, u0 equal to directly limit of u of z as z tends to infinity. This is a limit of right hand side, which is 1 by z into bracket 2 plus 3 by z plus 4 by z square whole divided by 1 minus 3 by z whole cube. Now wherever something divided by z is there, okay, you are going to get infinity. So this is 3 by infinity, 4 by infinity, 3 by infinity is 0. So this becomes 1 minus 0 raised to 3, of course, denominator becomes 0. So totally this becomes 2, 2 upon again at last 2 upon infinity also becomes 0. So totally this is 0. Once again 3 by infinity is 0, 4 by infinity is 0. So this becomes 2 plus 0 divided by again infinity, 2 by infinity. So this is 1 raised to 3, 1 minus 0, totally 0. u1, limit of, we have to multiply by z to this number u of z minus u naught as z tends to infinity. Now let me take u of z as, let me take u of z as this part only. This I will replace it by u of z. So if I do that for u2, for u1, limit of z tending to infinity, z into, so 1 by z into bracket, okay. So what I should write into bracket? 2 plus 3 by z minus plus 4 by z square. This part I am writing. 2 plus 3 by z plus 4 by z square. Denominator is quite straightforward to remember. So which is, of course you can see and write, which is 1 minus 3 by z raised to 3. Now we can very easily observe that this part is getting cancelled. So remains is, this part is getting cancelled. So remains is limit of z tending to infinity of 2 plus 3 by z plus 4 by z square. With little practice, u naught u1 can be found using inspection, 3 by z raised to 3. Now when I put infinity as a limit, putting the limit, we get 2 plus 0 divided by 1 minus 0 raised to 3. So u1 ends with 2. Now let us come to u2 part. u2 is again limit, again z tending to infinity, z square to this main function u naught u1 by z. u naught is 0, u1 just now found 2, so limit z tending to infinity of z square u of z, let me write in the usual fashion, which is, if I write in this fashion, u of z, main function I will take. So let me take u of z in this fashion now, u of z in this fashion. What happens to us? Now u of z is 2z square plus 3z plus 4 whole divided by z minus 3 raised to 3, whatever is there, z minus 3 or z minus 4, minus 0 minus 2 by z. Now we have to take cross multiplication and take the limits. So when I do that, first of all we have to simplify this. Limit of z tending to infinity, z square as it is, denominator z into z minus 3 whole cube, LCM, z multiply here and z minus 3 raised to 3 here. So z into 2z square plus 3z plus 4 minus 2 times z minus 3 whole cube. In the school you have learnt a minus b whole cube. Your teacher could not have told that you will be using a minus b whole cube in z transforms. Whatever you have learnt, somewhere it will come to use. Sometimes even maths teacher may not be able to in the position to tell that this you are going to use further, because the opposite party will not understand this. Now z square by z, z into remaining z minus 3 whole cube as it is. Remaining, I will multiply it inside 2z cube plus 3z square plus 4z minus into bracket 2 into bracket a minus b whole cube, a cube minus 3a square b plus 3ab square 3 into z into 3 square minus 3 cube. Here what happens is, usually in such cases first terms get cancelled, 2z cube and 2z cube get cancelled, remaining terms remain as it is. This is equal to limit as z tends to infinity of z by 3z square and here z square term is there, minus 9 minus 2 plus 18 plus 3. Shall I write 18 plus 3 z square terms as 21 z square you will get. Okay. Then next some z term, 4z and here 9 into 3 27, 54. So 4 minus 54 minus 50 z terms. Then some constant, minus 2 and minus 27 plus 54, okay, plus 54 terms, it's all, whole divided by z minus 1 whole cube. Now what happens is, here also z raised to 3 is there, here also z raised to 3 is highest. Now what I will do, I will take common like this, limit of, actually you can stop here, highest power is z raised to 3, highest power is z raised to 3. If you take the limits, 21 z cube divided by 1 z cube is actually in the range. In the numerator highest power is 21 z cube, in the denominator is highest power is z cube. We can definitely write 21, or else I will write z into z square out, remains in the numerator 21 minus 50 by z plus 54 by. So directly also you can write 21 if at all you can find it. Otherwise here also you take z outside, become z cube into bracket z minus, of course 3 is there, no problem, z minus 3 by z raised to 3. What happens is, both z cube and z cube in the numerator will get cancelled. Okay, this part gets cancelled. Remains is, when you make z tending to infinity, okay, only this part 21, this remains, 21 remains. Remaining all 50 upon infinity, 54 upon infinity, this becomes 1 minus, sorry, this is 1 minus 3 by z, 1 minus 0. So that this is actually z tending to infinity, cancelling this I will write 21 minus 50 by z plus 54 by z square whole divided by 1 minus 3 by z whole cube. When I put limit, except constant term remaining all will become 0, except constant term 0 in the numerator, denominator 1 minus 0, this part becomes 0 raised to 3, so u2 is 21. Dear students, very similarly, and like the last example, without fail you try u3, you should get 139. Now any example of this type is done in a similar way. Before I go to the inverse transformation, I would like to do some very two important examples. One is z transform of impulse function and z transform of unit impulse function. Two functions, z transform of two functions and unit step function. So find z transforms of unit impulse function. Now I'll first draw the unit impulse function. Impulse function is for a short time, that is of course here we are taking n, this is our u of n. Only for short time this un exists. For suppose n equals 0, it is existing. For short time this exists, and suppose the height is 1. Just like for a short time and clap like this. Before that and after that it is not there. Before n equals 0, after n equals 0 it is not there, means after n equals 0 the value is completely 0, means 0, 0, 0, 0 discretely like this. So actual function is once again I'm drawing for you. At n equals 0 some height is there, remaining all 0, 0, 0, 0 like this. So n u of n. Now what is the Z transform of this? So this is very straightforward, depends on the basic definition of Z transform. Z transform of any function is to that function you have to multiply z raised to minus n and take the summation. Z transform of this unit impulse function, okay, Z transform of this unit impulse function has got special notation, is u naught z raised to minus 0 plus u1 by z plus u2 by z square plus and so on. So here this is 1 into z raised to minus 0 is 1 and 0, 0, 0, 0. Very, very interesting and important for practical applications. Z transformation of impulse function is 1, or inverse Z transformation of unit 1 is impulse function. Never, 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 never forget. Never forget, please. I'll go to the second question of this category, and today this will be the last question for us. Find Z transform of unit step function. The name itself suggests that. First I'll draw the graph of that. Suppose this is n axis, this is un axis. Up to certain range it is 0, 0, 0, 0. Suddenly it becomes height 1 and remains constant like this. But here discretely it remains as 1, 1, 1, height is 1. So that is u0 is 1, u1 is 1, u2 is 1, u3 is 1. Now unit step function, if I take value of that unit step function is un is 0 for n less than 0 and it becomes 1 for n greater than or equal to 0. That is height is 1, 1, 1. All u0, u1, u2 and so on all become 1. So if at all we have got this much of knowledge, unit step means it comes like this, suddenly it takes a step one step up, becomes unit step and remains as it is. So now if I apply Z transformation of this unit step function is again to this un you multiply by z raised to minus n summation n equal to 0 to infinity. Expand it, u0 u1 by z, u2 by z square, u3 by z cube, and we know that. So almost we are coming to the end of today's session. All u0, u1, u2 values are 1, 1, 1. So it is a geometric progression. If you are reminded of some Z transform which you have already studied, this is if 1 plus r square plus r cube is there, infinite geometric series is 1 minus 1 by r. In this case r is 1 by z. So Z transformation of this unit step function is therefore 1 upon 1 minus r is 1 by z. With little simplification, Z transformation of unit step function is z by z minus 1. If you remember, z transformation of 1 was z by z minus 1. So both of them definitely match. So today we are stopping here. And all this knowledge in the next class we are coming from z function back to n function. That is known as inverse z transformations. So in the next lecture, tomorrow is our usual habit of telling when offline was there in online. In the next lecture, inverse z transformation we shall learn, and these two knowledges we can use for applied difference equations. So practice whatever is taught so far in z transformations. So n to z domain, z to n domain, how we are transforming, that you have to practice. And finally, almost 1.5 hours is remaining. Practice this third module again and again, taking pen and paper. Till we meet next time. Bye.